In this video, we're going to talk about what happens at the end behavior of a function on an infinite interval. So basically what the function looks like to the left and to the right, far left and far right. So what happens as x approaches negative infinity or positive infinity. So let's consider the function f of x equals negative 2x squared divided by x squared plus 3. So you can see from the graph that I've got here that it does appear to kind of flatten off as x approaches the left-hand side or the right-hand side. But let's take a look at this numerically. So I'm just going to plug in some numbers to the left and to the right. So I've plugged in some values for x and calculated the f of x value for each of those values of x. And you can see that as x increases, as it gets larger and larger, I just kind of increased it by powers of 10 here, we go from negative 1/2 to negative 1.941, and then you can see quickly we go to negative 1.9994, and then in this case we've got 5 nines and then a 4. So we can say that as x gets larger, f of x appears to be approaching negative 2. And on the left, you actually see the same exact behavior. So as x gets more negative, it looks like f of x is approaching negative 2. So we would write this behavior as the limit as x approaches infinity of f of x equals negative 2. And on the left, we would say the limit as x approaches negative infinity of f of x equals negative 2. So we haven't seen limits at infinity yet. That's where x is approaching infinity or negative infinity. So this is the formal definitions of those. If we let L be a real number, the statement the limit as x approaches infinity of f of x equals L means that for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. Now, we've still got this same epsilon greater than 0 from the normal definition of a limit, but instead of having x approaching c, we're saying there's some really big positive number m. Now think of the largest number you can think of, okay? And whenever x is larger than that number, f of x is approaching L. So there's some point at which f of x is arbitrarily close to L. Now on the flip side of that, if you're approaching negative infinity, we just say there's a negative n that's a really large negative number, such that f of x is arbitrarily close to L whenever x is less than n. Now the good news for you is that you will not be expected to be able to do any epsilon delta proofs for these definitions, so just be aware of it, but it's not something you're going to have to prove. But basically, another way of thinking about this is that the limit as x approaches infinity of f of x equals L means that for x greater than m, f is going to lie between L minus epsilon and L plus epsilon. So you can see that behavior. And it's going to happen on the right and on the left. Now in the previous graph that we looked at, as x increased without bound, the graph of f of x approached the line y equals negative 2. So if you can find a number like this where the graph is approaching a horizontal line y equals some number L, we call this line a horizontal asymptote of the graph of f. So the line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches infinity of f of x equals L. Now one thing that is very important if you are answering for horizontal asymptotes, just like vertical asymptotes, you must write y equals. If you don't write y equals and you just give me the number, that is not a correct answer. This is a line. It's not just a number. So keep that in mind, especially when you're working in WebAssign. So one thing that's important to note is that the graph of a function can have at most 2 horizontal asymptotes. You can have one from the left and one from the right. And unlike vertical asymptotes, it is possible for a horizontal asymptote to be crossed somewhere in the middle of the graph. That's because this is only really describing the end behavior. So you can have your function cross over that asymptote somewhere in the middle. So if we want to evaluate limits at infinity, they're going to have a lot of the same properties as the limits that we've discussed previously. So if you know that two limits both exist, then you can add them, you can multiply them, so on and so forth. Okay, the only place where this could get a little bit weird is when you're trying to divide limits at infinity, or if you're dealing with a limited infinity that also evaluates to infinity. So we'll talk about some of these scenarios. So this first theorem is very useful in evaluating limits at infinity. It says if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c divided by x to the rth power is equal to 0. So let's talk about why this happens. You've got some number that's a constant number divided by x to the rth power. Now this denominator right here is growing. It's getting larger and larger and larger because r is a positive rational number and you're plugging in something that's going towards infinity. So x to the r is also going to be going towards infinity. And you've got a constant numerator. So the numerator of your fraction is staying the same, but the denominator of your fraction is growing. So whenever that happens, that means the whole fraction is going to shrink. And if it shrinks enough, it's going to end up at 0 or approaching 0. It's never going to actually be equal to 0, but it will approach 0. And the same thing is happening if you have c divided by x to the r as x approaches negative infinity. It's just instead of approaching 0 from the positive side, it would be approaching 0 from the negative side. So let's look at some examples that you can evaluate using this property. So each of these limits use the properties that we've been talking about. So if I look at this first example right here, I've got a 45 and a 15 over x cubed, and they're being subtracted in the middle. So the limit as x approaches any c is going to be that. So the next three examples are going to use the rules that we've been talking about in order to evaluate some limits at infinity, or possibly negative infinity. So in this one, we've got the limit as x approaches infinity of 45. So this is a constant y equals 45. And all the way to the right of the graph, you could see that that would be equal to 45. This one is a c over x to the r, so it's going to have a limit as well. So this is equal to the limit as x approaches infinity of 45 minus the limit as x approaches infinity of 15 over x cubed. So this one is going to be 45. Again, here we have a c over x to the r as x approaches infinity. So that's going to be a 0. So the answer here is 45. Now, if you were going to take the limit as x approaches negative infinity of the same exact expression, again, you would have the limit as x approaches negative infinity of 45 minus the limit as x approaches negative infinity of 15 over x cubed. And this again is going to be 45 because it's a constant. And if you scroll back to the rule, it says the same thing is true for both infinity and negative infinity. So this is going to be 0 again. So this limit is actually also 45. And this one right here might not look like one of these limits at first, but if you rewrite that square root of x as x to the 1/2, you get that this is a c over x to the r for a rational positive r, so this one is 0, and that is the answer.